Hello, everyone, and welcome to this week's Secrets of Flow. I'm Alexei Zheglov, speaking from my place in Toronto, Canada. It's Tuesday, 12 o'clock noon, where I am. This is the usual time of the day and day of the week when I'd like to speak in a somewhat unscripted and improvised way from my mind on some important topic related to improving the world of work, particularly the modern work that involves a lot of technology, complex professional services, the work mostly invisible and difficult to manage, so that we can get better results for our customers, for our business, and of course for people doing and managing the work. And today, I want to talk about forecasting. When will it be done? Forecasting projects, deliveries, and I want to show today how far we can get with relatively simple, even low-tech tools. So the whole subject of forecasting doesn't have to be complicated, intimidating even. It is pretty simple. I also want to say, and this is the second important point for today, is that improvement and forecasting often go hand in hand. Very often, it's not just enough to, let's say, forecast or predict when we'll deliver something to a customer. Whatever work process we have for that often needs improvement. And maybe it's good and fit for customers' purpose today, but who knows about tomorrow? Customers' expectations may shift, there may be some trend happening in the industry, so the process actually does need to improve in the near future. And it turns out that if you know what it takes to improve it, that means you already have some knowledge, some kind of model that tells you something about your work. And that model is actually can serve a second purpose, which is actually forecast how your work process will perform in the near future. And the third important point I want to make today, and maybe this is really the most important of all of them, is the word forecasting is often used in our daily lives as in, let's say, forecasting weather. What's the weather forecast for tomorrow? Of course, we can check it on the internet. It will tell us the likely temperature, the probability of rain or snow. But what's interesting is that we don't really have any control over it. Right? Tomorrow's weather will just happen. And of course, it would help us to know if it's going to rain or shine or snow tomorrow. But whatever it is, whatever will happen, we can't really change it, right? So it's not like there is a tap that we can turn on and off to make rain or snow or to make it stop, right? However, forecasting your projects, or generally speaking, various work products of your enterprise or your team, is about changing what will happen, because you do have some control over it, right? So the project can, the project forecast or delivery forecast can inform us about what is still in our control, so that we could perhaps steer it towards a more optimistic outcome, such as if we want a warmer temperature for tomorrow, so to speak, we can actually make it happen, or at least increase our odds of making it happen. All right, so let's proceed. And I'll start with kind of an intriguing question. Here's a flag of the country. What country is this? Well, maybe it's not really important to know what country is this. This is not about answering trivia questions, but this is something I just something attracts me to this particular flag is that, well, it's interesting that it has a diagonal stripe pattern. Well, actually, several countries' flags do, and me being kind of a process improvement sort of person, I kind of look at this geometric pattern and I can't help but think it reminds me of a cumulative flow diagram. So anyway, actually, if your project is in a good, healthy state, if it's progressing steadily, well, actually, the cumulative flow diagram will kind of look like this. It will resemble this shape. Well, this flag also has 5 stars in a certain pattern. And what I'm about to show you is that, well, sometimes people say about success of uncertain enterprises, if the stars align, right, then our project will be successful. Well, actually, the stars don't have to align, but there are 5 important indicators, and we can express them as numbers. 5 important indicators of your project that do have to line up with each other, sort of like this 5-star formation on the flag. So let's talk about some project that we may be starting today, and let's talk about these 5 indicators. So let's go here, and let's start with simple things like, let's say, the scope of this project. So let's say we're just getting started. We broke down the project into a number of discrete, meaningful items, such as, reasonable people can make decisions like the starting order of these items, for example, because there may be some value in doing certain things earlier or later. So let's say our project has 120 work items in it. And let's say our target timeline for this project is 6 months. And what does it mean? We need to sustain the delivery rate of about 20 items per month. Is this very simple, right? This is this is very simple math. We just made a number of assumptions about our project. We can write them down in some kind of plan, and it has to end up like this. If we have somehow capacity to deliver 100 items per month, then perhaps our 6-month project timeline is just needless padding. We don't really need that much time. We could potentially deliver it a lot sooner. And if we only have capacity to deliver, let's say, 5 items per month, then of course this sort of equation is completely unrealistic. So these 3 numbers, in the most basic sense, have to align like this. But there is a bit more to this, and I hid the 2 other important indicators for now. Because let's have a look at, let's say, a visual management board, how this project is progressing at some point in the middle of a project. So the 20 items per month is the delivery rate that we should be observing right around this line, the finish line for our work items making up our project, right? So we should be seeing items crossing this finish line steadily. We should be able to measure this rate, and it should add up to about 20 items per month. And there are 2 other important quantities here. How long does it take to deliver one work item from start to finish, this particular cycle time, how long is this? Presumably it is much less time than the duration of the entire project. And how many items are in process concurrently? Well, right now this board shows, for example, 6 items, but I mean, it could be really any number depending on how you're managing your project. And it turns out that these 3 quantities, the throughput of the work process, that is basically the backbone of our project delivery, the cycle time of one work item, one of many in the project, and the number of these items concurrently are in a relationship known as Little's law. And if we divide one of these 3 quantities into another, we get the third one. So, how long does one item take? Do we have any indication? Well, we could actually measure it. And let's say, on average, we've got maybe, let's say 15 days. Or half a month. And now it turns out that if we took the number of work items concurrently in process and divided it by the cycle time of the item, we should get this delivery rate of 20 items per month. And that basically very simple math gives us that for the duration of the project, we should be able to maintain the concurrent rate of about 10 work items. So these 5 stars kind of aligned, and folks, this is a very basic sanity check around, let's say, the start of the project. So usually project groups and project managers are quite certain about how long their project should take. They may even have some kind of requirements document or some kind of scope document, some initial project plan that basically enumerates various requirements that are to be met. There could be some breakdown of the project into work items. There may be a backlog in some state of grooming that we could estimate and say, yes, it has more or less, let's say, 120 work items, the number I used in my example. So we divide these 2 quantities, we derive the delivery rate, and this is where things get interesting. Because in some project organizations, there's basically no evidence that any sort of team or project group actually exists, some work process actually exists, that is capable of delivering this type of things at this rate. And this is where the health of the project is immediately in doubt. Because the 2 quantities, 120 items and 6 months timeline, they imply delivery rate of 20 per month. If we don't have evidence such a thing exists, the plan begins to look less realistic. However, let's say we do have evidence of it. Yes, there is some department or group within the company that typically does this sort of things, and let's say they have some availability to take on new work and attain this kind of delivery rate. Let's have a look at how long it takes them to deliver just one of these 100 plus things. If it takes them close to 6 months, or even if it takes 3 or 4 months, well, that's a sign they may not have sufficient capability to deliver a whole bunch of these things in a timely manner, in a timely, predictable manner. But let's say, yes, the work items do take significantly less time, and let's say roughly half a month, a couple of weeks on average. then if we can work on 10 of these things concurrently with this cycle time, then the numbers kind of add up. Okay, do we actually have project teams, project group that can actually maintain this concurrent work for the next 6 months? Well, if it turns out that we have maybe a person here and a half person there, and of course we can put, 10 concurrent items onto their Jira board, that doesn't mean they will be working on all 10 concurrently. So that's an indication that the project group is understaffed, under-resourced, under-provisioned to actually take on this project. So you can use these 5 quantities to do some kind of sanity check. Is this project in like a reasonably good condition from the start, or some of these numbers are way off, and that would be a clear red signal that this project is in trouble from day one, and perhaps is even wholly unrealistic. All right, so however, now let's zoom out a little bit. What we just calculated is what I call the point forecast, because this is just one possible scenario for this project to end up. Because this is just one set of numbers. But all the possibilities of how this project may progress involve a whole ranges of numbers. Will the eventual count of completed work items be exactly 120, or maybe will be a bit less, or maybe a little bit more? And the thing is, we don't really know. So there is some error of estimation that we put on this number. Will our actual delivery rate, or the throughput of our work process, be exactly 20 work items per month, unchanged, constant for the next 6 months? Well, whatever is our method of determining this delivery rate, there is probably some error in it. And sometimes this reminder is necessary for a lot of people sometimes, but every time you make some kind of business decision based on a formula with a denominator and the numerator, when you take one thing and divide it by another, I should say one quantity, you take one quantity and divide it by another, the result is not a number. It is usually a little presumptuous for anyone to say that they know any of these quantities with an error of less than 10%. Do we really know that the delivery rate of our process will be 20 items per month? Are we so sure it cannot be 22 or 24 or 17, plus minus 10 or 20%? Whatever our measurements, whatever our recent observations of this process, there's no guarantee it will not change maybe a little bit in the future. So every time we estimate these numbers, there is some inherent error. And so what we just calculated is a point forecast. It just basically assumes no error. It assumes this precise number will actually happen in the future. And of course, if that number were to happen, that would be exact outcome. And this is like with the weather forecast. So let's say the weather forecast for tomorrow may be minus 5 degrees, but can it be minus 4 degrees, minus 3, or minus 6? Of course, right? So there is some degree of error in it. And so an important step we need to take is to move from a point forecast to a probabilistic forecast that shows us some range of estimates, and attach perhaps some probabilities of what will happen, such as with tomorrow's weather forecast, -5 degrees is actually quite likely, -3 degrees in Toronto is, well, it's January in Toronto, right? So -3 degrees is possible, +5 degrees is very unlikely, like +20 degrees, that would be my preference, is not going to happen, right? But on the positive side, -20 is not going to happen tomorrow, although it did happen before. So let's go to another tool. The probabilistic forecast is a bit more difficult to calculate on a napkin, so we are going to use Excel. So let's make some, and I just opened book 1. This is just a blank worksheet, and I'm just gonna show you how far you can get in a matter of minutes. So I'm going to make a few assumptions. So how many items in the project? Okay, well, there was 120. What was the throughput of our work process? Oh, it was 20 items per month. Sorry, for some reason this is a percentage field. It should be a number, so 20 items. Is there some kind of error in our estimation of throughput? Okay, perhaps 10%. And are we sure that the number of work items will actually end up with 120? What happens very often in real-world projects, and this is particularly true of knowledge work, work gets completed in knowledge work often means new information gets discovered. And that can change our understanding of what it takes to satisfy the same requirements of the project, and that can basically mean a different number of work items. Also, during the time that our project continues, all sorts of events can happen. They may potentially obviate the work items we already delivered, and that effectively pushes up the eventual count of work items. So let's make some assumptions, such as, let's say, maybe that count will stay the same, or maybe it will increase of, let's say, maybe by 50%, which is not an unusual unseen number. All right, let's now simulate. This is a very simple probabilistic simulation. I'm going to toss a random number, and I will simulate basically how many actual work items will be when it's all said and done, how much throughput we will actually observe on average for the duration of the project, and that starts with our initial assumption of 20, and it has some embedded error in it. And that will give us an estimate of the duration of the project. We can calculate it, and then we can easily repeat the process, because of course an electronic tool like Excel allows us to run these formulas in a split second as many times as we like. Alright, so let's simulate the count of work items. So I'm going to start with, let's say, the number that's given to us in the initial estimate. And I'm going to, okay, so now I need to take a random number. So the function rand returns a random number between 0 and 1. And now I need to scale it to cover basically the interval between the best and worst case. And the best case is that actually, let's do it like this. So let's simulate the expansion. So we'll do it like this. It's a random number, and the random number should apply to the gap between kind of the worst case of expansion of the work items, which I just configured here in the cell B5 to be 50%. So, and the minimum. So And of course, we need to add the most optimistic, the lowest case, which is before. And so this is our just one simulated random number. Can we please make it with fewer decimal points? So, right, okay, so just copy paste. I'm just creating a column of numbers. So there are all sorts of simulated numbers. All right, so now we can simulate how much our project actually expanded. And we can do it by taking the initial estimated count of work items, and we basically apply the expansion percentage to it. And this is, again, a column of simulated random numbers. Okay, now let's do the same for throughput. So I'll use the initial assumption of 20 items per month, and I'll throw a random number, and that random number should apply to, of course, we need the interval scaled like this. And actually, let's simulate throughput error first. That would percentage. That will make the whole exercise a bit cleaner. So the random number, and so the random number returned will be between 0 and 1. So, and I should apply it to basically twice the width of the error interval, so on the minus side and on the plus side. So that's what it takes. And I should add the basically best case, the lowest estimate of throughput, which is of course unity minus whatever the error percentage. So let's make sure this is properly formatted as a percentage with right, so this is roughly the throughput we get. Yes, it's relative to the baseline. So it's all within plus minus 10%. So this is relative throughput. And now the actual throughput. The actual throughput will be, okay, this number, 20 items per month, times this relative percentage, and so here it is. So in some cases we'll see 19 items, sometimes 21 and whatnot. And now we're going to estimate the duration of the project under these changed assumptions. And again, this is a very simple estimation. And now I'm going to let's actually create a whole bunch of these data points, because we can just very easily copy and paste and create like 1,000 of these test runs. So here it is. It's exactly 1,000. And now I'm just gonna plot the histogram. Right, so here's our, let's make it a bit neater. This is our project forecast. Let's make it a bit nicer. We don't really need the axis on the left side. It serves no purpose. And also, let's format the horizontal axis so it's more readable. format access. So let's make a bin width of about 0.5, so that's half a month. And let's say our most optimistic scenario seems to be right around 6 months, so I'll set the underflow bin to 6. All right, so project forecast. Let's remove all this garbage. Forecast in the months. All right, so folks, this just basically took us a few minutes, and we can see basically the range. So with various, we basically error tested our initial project assumptions. What if its count of work items will increase by such and such percentage, which we don't know, but we kind of bounded within some range of assumptions. What if the throughput or delivery rate of our project team will be, well, not exactly 20 items, but plus minus some error percentage? That basically produces a broader range of scenarios. So our initial point forecast fits somewhere in this range, and you can see it's a fairly, it fits kind of on the optimistic end of it, right? And so the value of that initial point forecast on the napkin was that if those numbers don't add up in the optimistic case, I mean, the project plan is clearly not realistic. However, the probabilistic forecast is just a whole bunch of such numbers for all kinds of scenarios, good and bad, pessimistic, optimistic, mid-range. And we can see this range, and we can also see some probabilities attached. So the taller bars on this chart, that's just the number of times that particular outcome, such as, let's say, the project is delivered between 6.5 and 7 months, which is for the tallest bar. That's the number of simulations, how many times we actually saw that particular observed value. So the taller the bar, the higher the probability of that exact outcome. So we can see that mid-range outcomes are all between 6.5 and 8.5 months in this case. And folks, now I want to say about something about how sometimes in the field of forecasting, people who can do these kinds of metrics, why they sometimes attach a particular value to, let's say, higher percentiles of outcomes, such as, let's say, 80th percentile means in let's say 100 simulated scenarios, 80 out of 100, 80 most optimistic, better ones. The delivery took less than a particular threshold, and the other 20% were kind of on the other side of the threshold, so on the pessimistic side. So that's the meaning of the 80th percentile. So forecasters often give ranges such as at the 80th or 85th or the 90th percentile, and the question arises sometimes: is there a particular magic to that number? What does it really mean? And I would say there is no magic, but there is sometimes a very practical consideration. If we want a 100% guarantee that, let's say, this batch of work items will be completed before, a certain important date, or in no more than this duration of time, then we will have to pick the safe threshold very far into the future. And so there is a certain inflection point, and for some project groups it may be at their 80th percentile, for some at the 90th, and whatnot. But basically the difference between, let's say, 89% and 88% and 89%, it could be like months. And in the real world business, this is not always an acceptable trade-off. And so, as a rule of thumb, and this is where perhaps there is some magic in the number 85, is that if you calculated a somewhat pessimistic point forecast. And it's very similar to, let's say, the alignment of those 5 numbers, except that you would have to assume maybe a larger number of work items somewhat pessimistically. You assume a somewhat slower delivery rate, again, somewhat. You have to err on the pessimistic side, basically. And perhaps somewhat longer longer duration of individual work items. So you make you assume somewhat you take somewhat pessimistic stance with the project forecast, and you end up with a point forecast that fits somewhere, let's say, at the 80th or 90th percentile of this range. And now you're meeting with your customer, a stakeholder, and you're telling them, okay, yes, we know there is a kind of an optimistic scenario for this project. It's going to take this many months, and there is a somewhat pessimistic forecast that it's going to take this many months, and it's a longer period of time. But let's say by your customers' fitness criteria, this is still good enough. This is an acceptable timeline. And they understand that in a realistic case, which may be better than your pessimistic forecast that you just showed, they will get their deliverable sooner, right? So, but this pessimistic, or sort of what they can see as a worst case scenario, is still acceptable to them. This is when you should take the deal. You don't push for the absolute safety of, let's say, the 99th or 98th or 99th or 99.9 certainty in delivery. You basically, because that may very well push the timeline outside your customer's tolerance. But if they're tolerant to, let's say, your 80th percentile point forecast, that might be where you just make the deal and you go ahead with that project. But now you know what assumptions are embedded in your point forecast, and you can do something to perhaps steer your project towards a more optimistic delivery. You will, of course, have to control how many items you end up with. You can do something to make sure that that number doesn't grow too high. You can do something, again, in your control to make sure that you maintain a certain rate of delivery, that it doesn't drift into towards a lower number, right? That would extend your timeline, and so on and so forth. So those things are in your control, and you basically start your project with an acceptable state, and you keep steering it towards the more optimistic scenarios as it progresses. So that's the meaning of probabilistic forecasts, and within the probabilistic forecast, if we don't have capacity to calculate the full set of probabilities, we can do with just 2-point forecasts. Let's say one mid-range or optimistic, just like what I showed you with 5 aligned numbers at the start, and then a more pessimistic forecast, but which may still be acceptable to your customers. And that project basically has the same 5 numbers, except you make more pessimistic assumptions there just for safety. And another thing I wanted to do today, and we still have some time, is what about individual work items and their delivery timelines? And it turns out you can simulate it as well, and it doesn't really take all that much time or difficulty. And let's just make a very simple simulation. Let's say we're starting some work item today. It's some amount of collaborative intellectual work, solve a problem, deliver the result to a customer. And let's make some simple assumptions about it. Let's say it's going to take us between, let's say, 3 and 5 days of effort. right? And right away, I'm just gonna start simulating some random numbers here. So I'm gonna toss a random number, and I'm going to apply it to, let's say, the interval between the longest and the shortest effort. And so this is my simulated effort, and right away I'm just gonna throw a number of random numbers here, so we can see they're all in the range of, let's say, 3 to 5. All right, let's say we also have a some kind of process gate in this process, or non-instantly available resource, and let's say it can cost us up to a week. So, well, maybe sometimes it is instant, in which case it costs us nothing. And in some cases it's not available for a week, and it basically blocks the progress of our work item. So again, I'm going to throw a random number, and I will basically normalize it to this interval. And now we have some simulated numbers, how much this particular non-instantly available resource cost us. And let's say we have some kind of blocker that may occur in the process. And let's say it occurs with a probability of 50%, and let's say it costs us how much? Let's say it costs us, again, between 3 and 5 days. Alright, so let's simulate the effect of this blocker. So we need to do a little bit of logic here. So if the random number, so we throw a random number, and if this random number is less than this threshold percentage, 50%, the blocker occurs only 50% of the time. So in this case, we need to simulate the impact of the blocker, and the impact will be, in the best case, it will be this minimum duration. And in the worst case, well, we throw another random number, and we scale the interval between, we scale the interval of random numbers between 0 and 1 to the actual interval of possibilities. And of course, if the blocker didn't occur, it cost us 0. Alright, so we just simulated a bunch of numbers. Some of them are zeros, some of them no delay, and some of them are some non-zero amount of delay. And let's also simulate a dependency on, let's say, some external service that is external to our work group. And let's say it occurs with a certain probability, and let's say it costs on average certain amount of time, let's say 7 days. Okay, so as far as dependencies, they tend to have a certain probability distribution around that average, and so I'm going to build that in. So, but first we have to throw one random number to see if we actually hit the dependency. So I'm just not hard coding the 30% into the formula, just using a configurable cell in the Excel. In this case, it's a cell B14. Now, if value is true, we'll see how do I convert the random number between 0 and 1 into this. I think I have to multiply it by the average, and then I think it's, actually, I think the formula is this. Trying to remember it from by heart. I think it's this. Yes, and if it doesn't cost us, if we didn't hit the dependency, it cost us 0. I think I forgot the parenthesis somewhere. A random number. Yeah, I think now it's a complete. Why is it? Okay, where did I miss the parenthesis? Ah, there's an extra parenthesis here that isn't really needed. All right, and let's simulate the impact of dependency. Okay, of course we have to multiply it by this. All right. Okay, so now let's calculate the total. It's just simply the sum of all 4 factors that we have in our model, the effort and several probabilistic delays. And you know what I'm gonna do now? I'm just gonna do a giant copy paste, because you can see how quickly it takes. Modern computers are quite fast, so producing, let's say, 10,000 simulations of this work item takes almost no time. And now let's show the histogram. So that's basically when our work item will be delivered, in days. So I'll just make the I just want to make the horizontal axis a bit nicer. So let's use maybe 4 for the underflow bin. All right, so we've got our forecast. So I'm just gonna make it a bigger chart, like this, so that you can see it better on the screen. So this basically took minutes to build. And we can see the distribution of probabilities quite easily. And we can see it's not an entirely predictable process, and some like outlying outcomes of it could be quite frustrating to customers and may not be actually fit by their criteria. And this is kind of how this process performs right now. And as I said at the beginning, I want to and I want to emphasize this important point again. The point is not to predict what our process will do in the near future. The point is ultimately to improve it, because what we really need going forward is improvement. We need a better way of delivering our solutions to customers than the capability we have today. We need to keep improving, right? And this is more important than calculating with whatever degree of precision the performance of an unimproved process, right? Whatever, including some of the frustrating outlying performances that this chart shows. However, let's say you know what it takes to improve the process. Do you know what it takes? Well, if you do, you probably know that it has this recurring source of blockage in it that affects roughly half of all work items and costs you several days when it happens. That it has a dependency on an external group that affects roughly a third of work items. And when it happens, it actually costs you a fairly unpredictable amount of time. And there is also a non-instantly available resource, and if it's not available at this instant, then it costs you, again, some amount of time. And so if you are ready to improve your process, you probably know all of these things already because you have observed them. Maybe you saw them on your visual management board, or if you have a Kanban board, maybe you've seen those blockers and you've seen those days, items spent in certain days because, well, of a non-instantly available something. So, however, if you know all of those things, you can actually that very same knowledge allows you to forecast the near future performance of this process, just like what we did in a matter of minutes with a few manipulations in Excel. So improvement and forecasting go hand in hand. And I just want to show in the remaining minutes, I want to show some other interpretation of this. And what I'm gonna do for this, I'm just gonna clone this chart. Yes, and what I'll do is I'll actually throw away most of these simulations. So let's just get rid of all except the last 50 of them. Now, look at what the chart looks now. So it's a lot more ragged because we actually don't have thousands of data points to give it a smooth shape. And it also gives us kind of interesting signals, like there's some, let's say, multiple peaks in it. And also, I just want to hit a button in this Excel chart. And just with one click, I just regenerated a whole new data set, right? So you see how the previous chart is different than this one, right? And let's say you bring these two charts to your successive monthly review meetings. And then you say, oh, our process performed like this, and now it performs like this. And actually, the chart I'm showing you right now may actually be just accidentally look better than the previous one, right? So it actually, there's kind of a concentration of data points on the left that might indicate an improvement, a faster and more predictable process for the majority of our customers. And you basically show it as, look, we have improved. Now, of course, you realize that all I just clicked, I just made one click in Excel to simply regenerate, simply rerun the simulation. So the underlying system, the process is exactly the same. And if I just resimulate it a few more times, you can see how it very easily changes from time to time. And so if all we look at, like actually this collection of numbers, if let's say we actually got them by observation, it does tell us something about the performance of our process, right? It actually doesn't tell us much about what is going on the inside so that we can improve it. So we can start with this set of numbers, but then we don't actually forecast using these numbers. We need to look inside the process and to know what sources of delay exist in it, what blockers, what dependencies, what non-instantly available resources, so that we can do something about them. And that basically leads to a lasting improvement. So, for example, if we were to go back and make some changes, such as, let's say, our non-instantly available resource maybe becomes available a bit more reliably. If, let's say, we hit our, let's say, somewhat unreliable dependency less often, or maybe we figure out, let's say, a service level agreement with that external group so that they can deliver to us a bit faster. So I just basically just made a few changes, plugging different numerical assumptions into the simulation, and you can see how the chart basically shifted to the left towards the more optimistic, more predictable, faster delivery. So again, the forecast is based on knowing some real factors that affect your process, knowing some physics of what's happening inside your process. But the very same knowledge allows us not just forecast what, like basically tomorrow's weather based on yesterday's weather. It allows us to pull some levers and actually improve the delivery. So, folks, this was a very busy hour. We went through a whole bunch of things. Yes, when I try to live code this in Excel on the video, it may take a little bit longer, and I'm sure spent more than a few minutes on this today, longer than if you actually were to do it in the comfort of your own office. But I just want to repeat the main points of what we talked about today. Forecasting doesn't have to be difficult or intimidating. We can get very far with pretty simple tools. Improvement and forecasting go hand in hand. Forecasting weather is about what will happen, but that's not the business you're in. Forecasting projects and other deliveries in your business is about changing what will happen, presumably for the benefit of your customers and your business and your people. And very simple things you can even do at the lunchtime on a napkin, such as how big is your project in terms of, let's say, number of items delivered. What's your timeline? What delivery rate you have to sustain if you have to sustain it? How quickly can you make the constituent work items in your project, cycle time, how many of them does your project group need to be working on concurrently? These 5 key indicators of your project must be in some kind of alignment. Right? And this is a lot easier to attain than, let's say, the alignment of stars in the sky. So best wishes on, let's say, your next project. And then finally, talking about what is not a project, but let's say a single work item, a single deliverable that goes through your work process on its way to the customer. We can also model that if we make realistic assumptions about the dominant factors affecting time, which often happen to be, besides a few days of effort, various delays due to dependencies on external groups, non-instantly available resources, and blockage. Again, knowing these factors, how often they occur, how much they cost you, allows you to do both, to forecast the delivery, so you don't have to just go by recently observed numbers without understanding what caused them, right? And at the same time, it allows you to start pulling some improvement levers so that the impact of your dependencies, non-instant availability, other sources of variation is smaller, and that basically enables faster and more predictable delivery. Thank you very much for watching. And until next week, this was Alexei Zheglov from Toronto with another episode of Secrets of Flow. Thank you so much. Have a nice day.